Hello students, so I'm here with the solution of the gravitation chapter test released for NEET students on NTA Abhyas 2.0. It's not 2.0, the app is still the same. I have named it as 2.0. So for this paper, my first word is avoided. This is not a paper for the NEET aspirants for at all. The students who are preparing for JEE Advanced or JEE can attempt it. It's not for NEET students. And if because I have done it, so I'm giving you my analysis. 8 questions were easy, 16 were medium, so these 24 were good, but rest 6 are not that easy. 2 are I have rated as bouncer. For question number 6, the calculation, I don't know how can you give such a close option for such calculation for NEET students, and frankly this is not a paper to be done in 30 minutes, 30 question. I don't know who select these questions. They don't know that this is being selected for NEET student. Frankly, it's not the paper ideally for the NEET students. I still say please avoid it, and if you have done it, so what I can say, if you score 60 plus, you have done a fine enough, and anything above 75 plus is very good in 30 minutes. In 30 minutes this score is fantastic for you. So let's see how to solve such paper. For the one question I am telling, I have not done the solution because they involve many terms. I don't think students remember those, so no point in me solving it when in the examination condition I know there will be hardly anyone who would be solving, and for such a paper there won't be any Shoaib Aftab for sure. There won't be 720s type of scores if such paper do come in the first question. At what altitude will the acceleration due to gravity be 25% of that at the Earth's surface? I remember this answer even, but let's say to start, the G should be G at surface by 4. So at any h height above, the actual formula is G mass of Earth into radius of Earth plus h whole square, that is G, that is 1 by 4 of G at surface, which is GME over RE square. So you cancel it, what do you get? 4RE square is equal to RE plus h whole square. So from here you can make it out taking the root on both sides. 2RE is equal to RE plus h, that is h is equal to RE. That is the formal solution. That's option B will be the answer. Okay, let me slightly increase the size of the pen. Okay, next. If a tunnel is cut at an orientation through the earth, then a ball released at one end will reach the other end in how much time? So I think like I remember, you all must be remembering, let's say if you make a tunnel like this, so what we have this is, let's say, the center of the tunnel, this is the center of the earth. If you displace it by distance x, what you get? You get the particle is attracted, so it would be towards this left wall. This normal will be exerted like this. The gravitational force, which let's say if I call this distance as r, this would be g m. M is the mass of earth, capital M, small m is the mass of particle, by r square, not r square, sorry, this is not the way, because what you say inside the earth, it would be g mm r by r cube. And what you do, you say this component will balance and the net force would be directed towards this position, which we call as mean position. And by proving that F equal to minus kx, you all remember this is time period is 2 pi under root RE by g. This is a very, very important result, and this is approximately 84 minutes that usually people remember. Even the answer for which the angular speed of the earth, so that the person at the equator feels weightlessness, is also the same. So this is the time period of the SHM. Now it is asking the time from one end to the other end. So I can say, let's say from minus a to plus a in terms of in the SHM. Let's say if I dropped it means this is the extreme position, mean is in between, so this would be negative to positive extreme, and you know negative to positive extreme time taken is half of the time period of the SHM, so that would be 42.3 minutes. So don't go in a hurry. Answer is not 84, it is half of that, because it is not asking the time period, it is just asking how much time it takes to go from one extreme to another. So it's a very important question asked many times in many exams. A satellite revolves in the geostationary. Geostationary means the time period would be 24 hours. Omega is omega of earth, but in a direction east to west. You know the earth rotates from west to east, but this is revolving from east to west. The time interval between its successive passing about a point on the equator is. So here what you will have, if I do the omega relative of the satellite with respect to earth, that would be omega of satellite minus omega of earth. Both are equal and opposite, so it will basically, the magnitude relative will become twice the omega of the earth. So time period relative to earth will become, you can say, t by 2 of the earth, that is, you can say it will cross in 12 hours the same point between a point on the equator. So answer would be 12 hours. A very nicely designed question. Next one. 2 point masses of mass 4m and m respectively, separated by a distance d, are revolving under mutual force of attraction. The ratio of their kinetic energies. So here we know both will revolve about their cm. Let's say this is 4m and m, so they will revolve around their cm, which will be closer to it. And let's say this is r1 and let's say this is r2. So we know r1 would be m2d, that is m into d over m1 plus m2, that would be 5m. So r1 is d by 5, so naturally r2 would be 4d by 5. So this is what we can have. This is d by 5, this is 4d by 5. Both will go in the circular path, and we know because both will always be opposite to each other, omega of both will be same. So both goes in same omega. Now treating them as a circular or rotational part, you can say kinetic energy I can write as half I omega square. So what we have, omega for both is same, so therefore what we have, k1 upon k2 would be I1 upon I2. And what is I1? I1 would be 4m into d by 5 whole square. I am treating them as point mass. Question is saying so m into 4 d by 5 whole square. So if you do this, this will come out as 4 by 25. This will come out as 16 by 25. So I think the ratio comes out as 1:4. So option A is the most appropriate one here. Next one. Calculate the force of attraction between two spheres, each of 1 kg, separated by 3 meters. Each separated by each has one mass and separation is 3 meters. So I can directly write F is gm square, because both mass is same, into r square. So g is 6.67 into 10 to the power minus 11, m square would be 1, r square would be 9. So 6.67 by 9. So what would you have? This would be, I can say, 7 point something. So 7.4 into 10 to the power minus 12. That is the option that I am looking at. That is the only one in 7 series. Next one. The radii of the moon and its mass is given. What is the acceleration due to gravity? So you know g at surface. You already know g, mass of moon upon radius of moon whole square, like that on the earth. So g is 6.67 into 10 to the power minus 11 into m of mass, which is what you have, 7.35 into, this is 7 into 10 to the power 22 upon rm square, that would be 1.7. 17 square is 289, so 2.89 into 10 to the power 12. So 11 and 12, that would be minus 23, and that is 22. So 10 to the power minus 1, I can better write it as 6.67 into 0.735 over 2.89. Okay, so it is too close for comfort. I don't know why they have given such a question. How will a student do this without a calculator? I am finding it too tough to go further, but let's try it out. I think there's no point in going ahead. It would be too much time consuming, so I'll leave it here. And the answer that they have given, I am taking at 1.696 meter per second square, but no point. This is simply checking your calculation, nothing else. There's no physics involved as such. No point in giving such options. Next, let us assume that our galaxy consists of this many stars, each of one solar mass. Okay, how long will a star at a distance of this is 50,000 light years from the galactic center take to complete one revolution? Take the diameter of the Milky Way to be 10 to the power 5 light years. So here solar mass, light years, I think no need student can attempt such a question with such type of calculation, because you will have to convert light year into meters. It's better leave it. There's no point, because you don't even know what is solar mass, the mass of sun. If you write it, there's no point. No one expects you to know what is solar mass and something. This is a question that have been seen by me before also. The solution is too lengthy to attempt, so better leave. No point for me to try to show that I can solve or you can solve. Better leave such question in examination, so I am leaving it. Next, two spheres of masses m and capital M are situated in air, and the gravitational force between them is F. The space around the mass is now filled with liquid of specific gravity 3. The gravitational force will be. This is a very common question. Just remember the most important feature of gravitational force is that constant g is a universal constant. It does not depend on medium or location or anything. So if you put any liquid or something else, the force between the two particles will remain the same. Two masses remain same. That change happens in electrostatics but not in the gravitational force. So that force will remain as F. It doesn't vary with that medium. There is no epsilon r type of thing that you use here. Next, two balls of radius r each are placed at a distance r apart. The speed of the ball when they collide. So first of all, when they collide, the actual distance between them won't be 0. The centers will still be separated by distance 2r. So by the time they go, what I can write, I can simply say ui plus ki equal to uf plus kf, taking both as a system, because we know the total energy will remain conserved. There would be no loss as such. So ui I can write as minus gm square by separation r plus initial is 0, final would be minus gm square upon the gap would be 2r plus let's say 2 times, because from symmetry both will have the same speed. So what do you have now? So 1m 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 I can cancel it. So what you have, this is put it here, what you will have minus gm by r plus gm by 2r, that is equal to v square. So v comes out as root gm, I can take common 1 by 2r minus 1 by r. So what we have, so substituting that negative sign inside, this would be option B, that would be the most appropriate one here. Again basic energy conservation that I have applied. Next, mass m is uniformly distributed only on the curved surface, okay, of a thin spherical shell ABC. Are 3 points inside the shell as shown in the diagram. Let the gravitational potential at point A, B and C be VA, VB and VC respectively. Then okay, so here the main important thing is just I'll let you first solve such profile. Let's say take this hemispherical shell and take any general point here, let's say point 0 comma y, let's say this point BP. The major argument that I will say, just tell me what would be the gravitational field due to this hemispherical shell at P and what would be the component, let's say like something. So what we can say, you know, if I put this shell completely, if I complete this sphere, the field at the P will be 0. And looking at the bottom shell, if I take any masses, let's say any symmetric masses like that, they will always be attracting it towards it. So by symmetry you can say the lower shell attracts it, so the gravitational field will be downwards, and because the net field is 0, I can directly say due to the upper part the field at the P must be upwards. That means at all these points the field must be upwards, it must be directed upwards, and you know the field always points in the direction of what you can say from higher to lower potential. So you can directly make it out, A would be at the maximum potential and C would be at the lowest potential. That is the best solution you can think of about this question. This is a very important thing to consider. It's a nice question. The mass of a planet is 6 times that of Earth. Radius of the planet is twice that of the Earth. If the escape velocity in the Earth is v, then the escape velocity is, you know, the escape velocity is root g mp by rp, root 2 gmp by rp. So for a general case, so that planet has the mass 6 times, that has the radius, that is twice. So 6 by 2, that is 3. So I can directly say escape velocity for that planet would be definitely root 3 times the v escape on the Earth. So the option A, that's a nice easy one for you considering the above questions. There are two bodies of masses, okay, what it is, 1 lakh kg and 1000 kg separated by 1 meter. At what distance from the smaller body the intensity of gravitational field will be 0? So what I'll say, let's call it m. So that will become, I think what it will become, 100. Okay, so from here at what point the intensity of the field will be 0? Definitely it will be 0 near it. Okay, so let's call this distance as x. So this would be 1 minus x. So for the field to be 0, what I can say, gm by x square has to be equal to g into 100m into 1 minus x whole square. So this m and g thing get cancelled. So if I take the root, I know x is less than 1, so no plus minus thing. 1 minus x by x is 10, so 1 minus x is 10x. So x comes out as 1 by 11. You can go for option C. Nice asked question, easy but asked beautifully. If W1, W2, W3 represent work done in moving a particle from A to B along the 3 different paths in a field, you know the gravitational field is a conservative field, so that's the easiest one for you. The work is independent of the path if the initial and final points are same. For a body to escape from the Earth, the angle which it should be fired, we know it doesn't depend on the angle, it would be same, that 11.2 or 11.3 irrespective of what angle you choose. If the moon is to escape from the gravitational field of the Earth forever, it will require a velocity of, definitely you know for an object lying on the surface the speed is 11.2 and that speed is independent of the mass of the particle. The moon is already far away from the Earth, so it is definitely not that much attracted as the body near the surface of the Earth, so its escape speed will definitely be less than 11.2 km per second for sure. So go for option B out of these 4 options. Next, if a planet was suddenly stopped in its orbit, supposed to be circular, how much time will it take in falling onto the sun? Now this is a nice one. Again, what you need to remember regarding this, if a planet was suddenly stopped, supposed to be circular, how much time will it take in falling onto the sun? सन तक गिरने में उसको कितना समय लगेगा, ये आपसे यहाँ पर पूछा गया है. Now you know, if the earth stops rotating or the planet stops rotating, let's say this was rotating and this was let's say your star or sun, what you have, if the planet stops, we know it's basically is going to fall down like this, and now you have to find this time. Now this is not going to be easy because the acceleration keeps on changing. It would be variable acceleration, so either you need to integrate, or usually the people tell, let's assume it to be an almost an elliptical orbit like this or a circular orbit like this. If you take this as an elliptical orbit, hypothetically this is the way the people usually tell, otherwise the way integration would be too tough to start. But what I can make it out, because it is going to travel like this, we know for the same semi-major axis the time will always be the same. So for the same semi-major axis, if this goes like this, the time will still be t. But here, because it is going to fall into the sun, the semi-major axis will reduce to half, and because it will reduce to half, the time period will become 1/2 whole cube. That would become what we can say, t square is proportional to r cube. So what we will say, t square is proportional to r cube. So if the radius of the semi-major axis a cube becomes half, the time period proportional to r to the power 3/2 will become half into 3/2, what you can say 1/√8 times. So it would be t by root 8, let's say the time complete. Complete means that is to complete this complete round. Now you need to complete it, or you need only the half part. You need only the half part. The time would be 1/2√8 times, and you can write it as √2 times 8 √2/8 times also. And rest all options are greater than that actual time period. They are definitely not going to be true. So we can do it like this. Otherwise, the actual solution I think would be too tougher to handle. This is the way to do it. Otherwise you can just remember or leave this. No point in focusing on such questions for more time. Now, your body of mass m and radius r falls on the earth from a great height. If capital M is the mass and capital R be the radius of the earth, where small r is r/100, then the acceleration of the body when it hits the earth surface is going to be. So what happens when it hits the earth surface? So the acceleration of the body, that is, it is in free fall, so that would be g. And what would be the g for it? That would be g mass of earth into distance, because it has its radius r, so its distance from the center of earth would be r plus r, that is r plus r/100, and you do this as a whole square. So what you have, you can write it as gme by r square, that is the small g or gs, what you write, or you can write it as g dash and write it as g, because they have written it like this, and it would be 100/101 whole square. So 100/101, you all know, using the binomial theorem, you write it as 0.99, and 0.99 square into gme by r square, and 0.99 square would be 0.98 using those binomial techniques. So 0.98 gme by re square, you can write it as 0.98 g. Go for option B. I don't think someone has designed it keeping in mind that he or she is designing for NEET exam. I think this is a good one for JEE. If suddenly the gravitational force of attraction between the earth and the satellite revolving around it becomes 0, then the satellite will, if the force becomes 0, you know it will go in a tangential path. So that's a nice one. That's a good question where you can just read and tick. When a body is taken from equator to poles, you know at the poles the g is more, so its weight slightly increases. So go for option B. A geostationary, and why, you know, because of the two things. One is what you say, the earth is not a perfect sphere, the pole radiuses are small, and second is the gravity, the rotational effect. The rotational effect reduces the g at the poles. Geostationary satellite is revolving around the earth. To make it escape, its velocity must be increased. For any satellite, you know the velocity orbital is √gm by orbit, and the escape speed at distance r is √2 gm by r. So for irrespective of geostationary or something, any satellite in circular orbit, the speed need to become √2 times, or you can say has to be increased by 41.4%. So it's a general answer for any satellite. If the earth's radius shrinks by 1%, keeping its mass same, the acceleration due to gravity is, you know, g is gm by r square. So for small changes, you know, so g is inverse to r square. So for small changes, delta g by g is -2 delta r by r. So because r is decreasing by 1%, so -1%, so it will become +2%. So it means it will increase by 2%. Go for option C. Next, satellite revolves around the planet as a time period t and orbital radius r. The mass of this planet is, okay, so what you know, you always remember this particular thing As per this, T square is 4 pi square gm by r cube. You remember all these things. So the mass, and this mass is the mass of the planet. So mass of the planet is 4 pi square r cube by T square and g also. So going by this, which is the option, only the D1 is appropriate. I think by dimensions also this one will also be only be coming. Next, the moon's radii is 1/4 that of the earth, mass is 1/80 of earth, g represents due to gravity on the earth, and on the moon is, so g you know is gm by r square. So what he is given, the radius is 1/4, so r square will become 1/16, and the mass is 1/80. So 1/80 and this is 1/16, so 16/80, so g will be g by 5. Go by option B. Typically you remember it as g by 6, but as per the data given in the question, it should be g by 5. Two equal masses m and n are hung from balance, okay, which scale pans differ in vertical height h. Calculate the error in weighing, if any, in terms of density of earth rho. Okay, because the height is given, what we can say, here I will write it as mg at the, let's say, first location. Here I will write m into g at the second location. Even it appears how it will balance if the mass is same, and if I take this distance to same, I don't know, but the thing that I can make it out is the g would be differing, so the error in the measuring of this delta mg that I can say is 1 minus 2 would be mg g1 minus mg2. what you can write it like this. And what would be that error? That error would be g1 I can write as g naught 1 minus 2, let's say h1 by r, and here I can write it as g naught 1 minus 2 h2 by r. Definitely h2 is at more height, so what I can write it, if I solve it, it would be mg naught into 2h by r. That is the error we will get. And what is g naught in terms of the earth's density? You know, it is 4/3 pi rho g r, if you can remember, upon 2h r. So that is what we will have. So r and r cancelled. So as per this, the only option I can make it out, it's like this. This appears to be the only one which can match, nothing else. I still don't know how it is matching, but okay, I can calculate the answer, but I don't know how I calculate it, because the arrangement seems somewhat typical. At what depth below the surface of the earth the value of g is the same as the height 64 km from the surface? So you know, from the surface, if you go x distance up and x distance down, x distance up, the fall would be 2x by r, here the fall would be x by r. So what we can say, at a height 64 km above the surface, the depth you have to go would be double means 128 kilometers. That is a very usual concept being taught to you, definitely by your teacher. Speed of planet in elliptical orbit with semi-major axis a about the sun of mass m at a distance r is, you know, total energy is minus gmm by 2a. At this particular point, potential energy would be minus gmm by r. So kinetic energy would be E minus U. So half mv square would be E minus U minus gmm by 2a, minus becomes plus gmm by r. So this m goes. So v comes out as what it comes out as, root 2 gm by r minus gm by 2a. That is what we can make it out. Okay, so that is going to be your answer. So what's the answer here? If I take it yes, if I am taking it rightly, this is coming out to be by semi-major axis. Okay, so this is which one should go for? We should go for which answer? Which one we will go for? Okay, 2 will come here also, I just forgot it. Okay, so this would be the answer, option A. So don't do such mistakes. This is option A. Many remembers this result also. Body is taken to a height of nr from the surface of the earth. The ratio of the acceleration due to gravity on the surface to that at the given altitude. So what will happen at that altitude? The g would be gm upon r plus h, that is r plus nr whole square, and g at surface you know is gm over r square. So this gm goes, g upon gs is, okay, you have to take reverse one, gs by g. So gs by g, if you will do, it will come out as r plus nr whole square by r square, that is 1 plus n whole square. So go for option A in this case. Again, not a tough one for you. Next, simple pendulum has time period t1 when on the earth's surface, t2 when taken to a height r, you know that g becomes g by 4, t proportional to 1 by root g. So t becomes half, so the t becomes half, so t2 is half of t1. So t2 by t1 you can make it out as 1 by 2, I suppose. T2 by T1 is T2 pi root L by G. G has become G by 4. Sorry. So G has become 1 by 4. So it becomes 2. I'm lucky that 1 by 2 is not given. It should be 2 because T is 1 by root G. So you can make it out. Next. Astronaut of mass m is working on the satellite orbiting the Earth at a distance h from the Earth's surface. The radius of the Earth is r while its mass is m. The gravitational pull Fg on the astronaut is. Okay. It is working on a satellite orbiting the Earth at a distance h from the surface. Radius is r while its mass is m. The gravitational force, you can directly write gmm upon distance from the Earth's center, which is r plus h whole square. So it would be like this, working on a satellite. So it is working on a satellite. So it would be option C, that is the most appropriate. I can make it out from this. Okay. Calculate the angular velocity of the Earth so that the acceleration due to gravity at 60-degree latitude. You know, at any latitude G is G naught minus omega square r cos square lambda. So for this to become 0, this omega square r cos square lambda should be equal to Z naught. At 60-degree cos square 60 is 1 by 4. So omega square r is equal to 4 G naught. That is what we can make it out. So what you need? What do you need now? You need the angular velocity. So omega square is 4 G naught by r. You can say omega would be 2 times root of G naught by r. So what we will have now, this is the value we will have. Okay, solving it, not a nice option, but no other option for us. So what we will have, 2 upon 100, I can take it out common and it would be 8. So 1 upon, oh, it is easy now. So 1 upon 400 radian per second. So 1 upon 400, what you will do, so it is 2.5 into 10 to the power minus 3. So if you do it, the answer comes out naturally. So this is the paper for you, and definitely it's not for a NEET aspirant for sure.